Hello everyone. Today I'm gonna start Buckingham pi theorem, which is a theorem that we use it very often in fluid mechanics problems to reduce the dimensions of the problems that we are investigating, and it gives a very good idea to develop some relationships for some problems in fluid mechanics, especially that the governing equations of fluids, for example, the momentum equation in differential form is a nonlinear equation, fully nonlinear equation. So driving equations that we can easily solve is difficult with using these governing equations. So what we do is we use this Buckingham pi theorem to kind of find some relationships between different flow parameters based on dimensional analysis. Okay, so the main principle of Buckingham pi theorem is as follows: an equation with k variables can be reduced to a relationship among k minus r independent dimensionless, so this is important, dimensionless products where R is the minimum number of, let me write it this way, minimum number of reference dimensions required to describe the variables. Okay, so R is the minimum number of reference dimensions required to describe the variables, and K is the number of variables for a relationship. And this theorem says that we can reduce that equation using K minus R independent dimensionless products. Okay, this is a theorem in general in any field of physics, and we are going to use that for fluid mechanics. It's very useful. It's very useful theorem, especially for if you do some experimental work, because you will understand at least the variables, the important dimensionless variables that you need to be careful about, and you need to measure them rather than kind of doing the whole study among the whole parameter space in the problem. So you can reduce your kind of parameter space search to a K minus R dimensionless products, okay, in the independent dimensionless products. So I want to explain this more with an example. Okay, so let's get started with an example, because this is going to help us a lot to understand this principle and how we should use this. So determine a suitable set of And for these K minus R independent dimensionless products, we call them pi terms, okay? So here I say determine a suitable set of pi terms for a flow inside a circular pipe, a circular pipe, okay? So here we have a pipe. So as you see, we are moving toward the pipe flows, and this is kind of an introduction for the dimensional analysis and the kind of pi terms that we are going to use for pipe flows, especially their major losses in pipe flows, okay? So let's see. We have a pipe here. Okay, so the fluid is going toward inside the pipe from here, so it has a velocity v. This is section 1. This is section 2. This length is L. The diameter of the pipe is D. The density and viscosity of the fluid are rho and mu. Let me show them with this color because these are specifications and properties of water. And then we have these pressure difference here between these two sections, which I show as P1 minus P2, the pressure drop over length, okay? So here I want to write something. We are interested in the pressure drop delta PL per unit length. Okay. So eventually we want to find this pressure drop, a relationship for this pressure drop based on the flow parameters, okay? Flow and fluid parameters. And we want to just use we want to use this Buckingham pi theorem to find that parameter, okay? So let's get started and see how we can use that. So the question is, what are the pi terms? So pi terms or dimensionless, let's say dimensionless numbers to describe delta PL. Okay, so this is the question. So let's get started. So now I want to give you some steps. So we go step by step. And I have kind of reduced the steps necessary compared to some other references that you may take a look at just because I have combined them into 6 steps. So if you see other references, they might have more steps, but I have kind of summarized them into 6 main steps that you need to follow to find these pressure drop dimensionless the pi terms for this delta PL, or in general any kind of using Buckingham pi theorem in any fluid mechanics problem. Okay, so step 1, you should list all relevant variables in the problem. Okay, so whatever you think that really might be physically relevant, this is very important because you need to have a very good intuition about the problem and physics, right? So for example, I want to say, okay, what is delta PL a function of what? What are the important parameters here where you see that? So the pressure drop, one thing that you can think of is, just think about it yourself, maybe pause the video a little bit and then think about this. But one thing, of course, this should depend on the velocity, right? We know that. So this is our guess that it should depend on velocity. What are other variables here that it depends on? Again, on the fluids. So this was for flow, and then on the fluid parameters like density, it should depend on the density of the fluid. You can say if the density is higher, your pressure drop should be also what? So it's kind of relevant to that, right? And then you know about the viscosity, you know if your flow is more viscous, your pressure drop should be higher, right? Because the friction is going to be higher in the flow, so it's going to reduce the pressure more. And then the other parameter is about the pipe itself, which is the diameter of the pipe. And I haven't written the L because they're already accounting for it here. It's the pressure drop per unit length, okay? So that's why I don't write L. But if it was a general pressure drop, then I should have also written L as well, because it also depends on, the pressure drop depends on this P1, like this P1 minus P2 also depends on the length, okay? So this is the first step. You just list all the variables that are important in the problem, okay? And then let's see step 2. So step 2 says, so before I go, again, this is an important, very important step, because you need to know really what parameters might really affect or influence this, the parameter that you want to describe, right? For example, you cannot say some irrelevant thing, right? You might also include all of them, but then if you do the experiment, you will see that they don't really matter that much, at least, okay? For example, I can say about, what else? Like, you can say, I don't know, the dimension of the room, right? It doesn't really matter if, or the dimension of, or like the air temperature here outside the pipe. I mean, it could be important, but it's not that much important. You can write it down and you get a parameter, but when you do it in the lab, you will see, oh, the effect is not that much important. Or you can say the viscosity of air, like it shouldn't matter, right? Because the flow is inside the pipe and it's like, it could be water or oil. So the fluid of that, the density of that fluid is more important. So here, you should try to write the most relevant variables in the problem so that you can find the most relevant and most important pi terms that really determine the pressure drop in this system, okay? And these are the most fluid mechanics, flow, and also the pipe dimensions that are really important for this problem, okay? So the second step is express each of them in terms of basic dimensions M, L, T, right? Which are standing for mass, length, and time, okay? So the first one is pressure. So pressure drop, which is pressure per length. So let me write it down. The delta PL is pressure per length and pressure is force per length area, right? Force per area. So it's going to be force length area. And for force, you know from also the first few lectures we learned this. Force is going to be MLT minus square in terms of basic dimensions, and area is L square and length is L, so it's going to be L cube. And so this is going to give me ML minus 2, T minus 2 is going to be the basic dimension of delta PL. The basic dimension of, let's see, V is LT minus 1, right? It's length per time. The basic dimension of rho or density is mass per volume, which is going to be mass per length cube. So it is ML minus 3. The basic dimension of density, viscosity, again, you can look at the notes we already had derived them before, is going to be ML minus 1, T minus 1. And this is coming from that tau equals to mu du over dy, right? So if you look at this one, this is going to be, this is force, this is stress, right? And then you have this, so based on this formula, you can derive the basic dimension of viscosity. And basic dimension of diameter is what? Is length. Okay? So we have already covered them in the first few lectures. I just rewrite them again, and if you have problems, you can go and see in that lecture how we can write any parameter in terms of basic dimensions. So the third step is, after writing this, step 3 is determine the required number of pi terms at according to pi theorem. Okay. So pi theorem states that the required number of pi terms is gonna be k minus r, where k is the number of variables and r is the minimum number of reference dimensions. Okay, so let's write them down. What are gonna be the number of those? So k here is what? The number of variables. How many variables do we have here? One is the delta PL, 2, 3, 4, 5, right? So we have 5 variables. So I write it down, k equals to 5, number of variables. And R is the number of reference dimensions, right? The minimum number of reference dimensions, which is what? Here we have it. It is 3. So it's number of reference dimensions, which is MLT. Okay, so k minus r is gonna be 5 minus 3, based on the pi theorem, is gonna be the number of products that we can describe this for. So the number of pi terms, we first find it here, so it's gonna be 2. So we are gonna have pi 2 terms required to describe this delta PL based on the pi theorem. So this is how pi theorem helps us to find the number of required dimensionless numbers, or we call them pi terms here. Okay. So then the next step is, so step 4, select a number usually 3 select a number of repeating variables. Why it's usually 3? Because of the dimensions. The basic dimensions, we usually, in this problem, set of problems, we have 3 main dimensions, basic dimensions, MLT. And so we typically use 3 repeating variables, okay? But we want to use the repeating variables such that each of them has at least one different dimension. So we want to kind of account for all the 3 basic dimensions using these variables, okay? So we usually don't select delta PL, which is the simplest and not a dependent and not an independent variable. So it's a dependent variable, right? We want to find the dependency of delta PL to all these variables. So we usually use one of these three of these as the repeating variables. So what I'm going to use is the simpler ones. So I want to use V, rho, and D as the repeating variables, okay? So we choose D, V, rho. It should be usually simplest variables. We don't want to like go with viscosity is a little bit more more complicated, has more complicated dimensions. This is gonna make our calculations simpler. So simplest and variables and not the dependent variable delta PL. Okay. Okay. So step 5 is form pi terms by multiplying one of the non-repeating variables by the product of the repeating variables with exponents to make them dimensionless. To make them dimensionless. Okay, so let's do that. So this is where we write the pi terms. Okay, so the first pi term is pi 1, which equals to, so first what are my non-repeating variables? My non-repeating variables are, first is delta PL, the second one is mu, right? So the first one, I'm gonna multiply that delta PL by the repeating variables, so D, and then with exponents, I have to do it with exponents to make them dimensionless. So D to power A, D, V to B, and rho to C. Okay, so this is how I do it. And then the second pi term is going to be the second non-repeating variables. But now I want to make this pi term a dimensionless number, because this is what also is said here, a dimensionless product in the pi theorem, right? So I have put this these exponents to make these dimensionless. Okay, so in order to do that, we already have the dimensions of all these variables. So I just copy them. We have ml minus 2t to minus 2 for the pressure. So I just write it down. I want to make this dimensionless. ml minus 2 t minus 2, then multiplied by d. The dimension of that is length to power a, so L to a, and then the dimension of velocity is length per time, so LT minus 1 power b, and then the dimension of density is mass per length cube, so ml minus 3 to c. And I want to make this dimensionless, so the dimension of this should equal to m to 0, L to 0, and t to 0. Okay? So this is going to give me 3 equations for each of these dimensions. So for m, we have the first term is 1. We have from here And then we have also m here is plus c, right? So plus c should be what? The right hand side of the equation should be 0. I write this for exponents, right? So for exponents of m, so let me write it down here. For exponents of m, okay, we have this. And then for exponents of the second one is for L. We have what? The first term is minus 2. And then we have here A plus A. Here we have B. So plus B. And then here we have minus 3C, right? So minus 3C equals to 0. And finally, for compound exponents of t or time, we have minus 2 minus b equals to 0. Okay? So this one clearly, the third equation gives me b equals to minus 2. The first equation gives me c equals to minus 1. And then the third equation, the second equation gives me minus 2 plus a minus plus b, which is minus 2, minus 3c, which is going to be plus 3, equals to 0. And so a should be 1. So these we have found from these equations. So we found the first pi term. So the first dimensionless pi term is going to be delta PL times d to power a, which is d to power 1, over v to power rho to v to power minus 2 and rho to power minus 1, right? So times rho minus 1 and v minus 2. So I just write it in the denominator. So it's going to be rho v square. Okay. So this gives me the first pi term or dimensionless number. This is dimensionless. You can calculate it. It has no dimension, and it's very great because you can use it in any unit, and you can measure all of this in any like in either British or System International, and it's gonna give you a dimensionless number. So it doesn't matter if you use British system or the international system. And then we want to find the second pi number. So the second pi number, pi term, or pi 2, is we have to multiply again the other non-repeating variable which we had, which is mu or viscosity, by all the repeating variables, which is d with their exponents to make it dimensionless. So d to a, vb, and rho c. So this is non-repeating. And these are all repeating variables. So now I can write this again. So let me write it here again. But only the first term, the dimension of the first term is going to be different. So I'm going to clean that. So what is the dimension of the first term, or viscosity? The dimension of viscosity is shown here, ml minus 1, t minus 1. So I have ml minus 1, t minus 1, and then multiplied by d, the dimension of that is length to a, velocity is lt minus 1 times the dimension of power b, to p to b, ml minus 3, which is the dimension of density, to power c, equals to m0 l0 t0. So this is gonna give me three equations again. So for m, we again have, let me write it down. So for m, we have m, which is 1, plus c equals to 0. For L, we have minus 1 plus a plus b minus 3c equals to 0. For t, or time, minus 1 minus b equals to 0. So this gives me, the first equation gives me, the last equation gives me b is minus 1. The first equation gives me c is minus 1. And the second equation gives me minus 1 plus a plus b, which is minus 1, minus 3c, which is going to be plus 3, equals to 0. And so a is going to be minus 1. So the second pi term is pi 2 equals to mu viscosity, and all of them are going to go to the denominator with power 1, right? dv rho. So this is second dimensionless number. Okay, and based on the pi theorem, we have two pi terms, or two dimensionless numbers in this problem that we found them using the dimensional analysis. So pi 1 and pi 2, which are shown here. And finally, the last step is step 6. Express the final form as a relationship among the pi terms, and think about what it means. Think about what it means physically. Okay. So finally, you have to relate these two dimensionless numbers. So on the left-hand side, I'm going to say what I'm going to do is you write the dependent variable that you had, the pi term of that. So it's going to be pi 1. So let me see if I can copy. Let me see if it is doing correctly. No. So let me just write it down. So this delta p L times d over rho v square, and then you wanna define a function of the second dimensionless number. So this is gonna equal to, so here we had a general function f, and now we have a function, we call it as phi. of the second dimensionless number, and it could be more dimensionless numbers here, right? So this is going to be always your dependent variable on the left, and on the right are going to be the other dimensionless numbers. So the first one should have the first dimensionless number that we write in the left should have the dependent variable that you are seeking, for example, delta PL here. And this is going to be a function of phi of the second dimensionless number, which is mu over dv rho, and because I can also write it as rho v d over mu, it doesn't matter. The reason is because this is going to also be a dimensionless number, right? Rho v d over mu. It's the same thing as this. If you calculate it, you will see that it's going to be also a dimensionless number. So this is how I want to express this final form between the pi terms, okay? So now I want to make some interpretations. What does this relationship mean? I have found a relationship for delta PL. Let me write this correctly. So delta PL and other variables, the fluid variables and pipe variables. So I want to see what does this mean. So this means that this problem, or finding this delta P, the pressure drop in a pipe flow, can be studied in terms of these two pi terms, or dimensionless numbers, rather than the original five variable the five variables that we started. So instead of this function, right? Instead of relating this delta P to all these functions, measuring all of them, what we can do is we can just calculate these two dimensionless numbers and then study this problem. And this is going to give me the function delta PL. So in other terms, for example, if you do this you want to do this in lab, what you want to do is, on one axis, you will have two axes for each of these dimensionless numbers. So on one axis, you will have pi 1. You write pi 1, which is delta PL d over rho v square. And on the other axis, you write and you plot pi 2, which is rho v d over mu. Okay, so if you do it in the lab, you measure density, the density of that fluid, the velocity of that fluid, the pipe diameter, the viscosity of that fluid, and then you also measure delta PL, the pressure drop, in two sections. And then based on that, what you want to do is you measure for different velocities, say, you will find different pressure drop, okay? So you, for example, for this velocity v1, if it is here, you find 1, you just kind of plot that. Then for the other velocity, you find another thing. For the other velocity, you find another point. And for another velocity, you find another another one. And so this is going to give you a relation, right? This is going to give you all the points. And if you kind of connect them to each other, what you are going to get is something like this. Let me do it with black. You will get a curve like this, right? After you do it and connect all the dots, you will get something like this. And so this is actually this phi function, right? So you can find this phi function from the experiments. And this is going to give us a phi function if we do that. So this is phi function. And so we have kind of reduced all that problem, all that kind of difficult problem into this simple, by using this dimensional analysis into this simple graph, where we can actually measure that in a lab and find the important variable. So this is very important because especially for nonlinear problems, you're going to use a lot of these dimensionless numbers to be able to find, for example, the losses in pipes, in other things, based on these dimensional analysis, okay? Because these fluid problems are all nonlinear, and we can use these dimensional reduction to be able to find all the relevant problems and showed and kind of find a relationship based on the experiments, okay? So let me just briefly overview. So in the next session, I'm gonna solve another example of using pi terms. And then after that, we are gonna look at some common dimensionless groups in fluid mechanics. And after that, we go to the next chapter where we start laminar or turbulent flows. And after that, we will talk about major losses and minor losses in pipe flows, and we will focus on single pipes and multiple pipe systems, okay? So let me briefly overview what we learned today. So today we talked about the Buckingham pi theorem, which states that equation with k variables can be reduced to a relationship among k minus r independent dimensionless products where r is the minimum number of reference dimensions required to describe the variables, okay? Then we solved an example. We wanted to find the pressure drop in this pipe. And then so we had all these dimensions, L, D, also the density, viscosity, and velocity of the fluid. So step one, you have to list all the relevant variables in the problem. Then step two, you need to express each of them in terms of basic dimensions, M, L, T. Step three, you determine the required number of pi terms according to the pi theorem. So k is the number of variables, which is 5 here. R is the number of reference dimensions, MLT, which is 3. So the number of pi terms that we need is going to be 2 pi terms, k minus r, which is pi minus 3. Step 4, select a number which is usually 3 of repeating variables, and we typically use the simplest variables and not the dependent ones. So this is going to be d rho v here. Step 5, form pi terms by multiplying one of the non-repeating variables by the product of the repeating variables with exponents to make them dimensionless. So this is what we did here, pi 1 delta PL times dA, b to b and rho to c. And then we always get some equations that we need to solve, and this gave me this first dimensionless number. And for the second pi term, we multiplied mu, and this gave me the second pi term, which is shown here. And finally, we have to kind of relate these to each other through a function phi, and then try to think about what it means. So this is what we did, and it means that this problem can be studied in terms of these two pi terms, dimensionless number, and then we can, in the laboratory, we can just plot something like this to be able to find the relation between the delta PL and velocity, right? So This is kind of the main approach we are going to use for many of fluid mechanics problems.